So yesterday we spent most of the time talking about kind of what a titration curve is, how we handle from a buffering standpoint, from an overall standpoint. What do we do when we have an acid-base system that we're adding acid to constantly, or we have an acid-base system that we're adding base to constantly? And this is kind of where we end up. Is we talked about with strong acids and with strong bases, and showed that we could use modified ice tables, basic stoichiometry, to figure out how much hydronium was left over, how much hydroxide was left over, and calculate the pH that way. And we brought up the ideas of what a weak acid titration looks like. And for those of you that were in lab yesterday, you got to see kind of firsthand what that looked like from a graphing standpoint when we did it experimentally, and kind of the differences that we saw between the strong acid curves and the weak acid curves. Well, now we're going to start to look at the 4 regions of the weak acid titration, and we're going to start looking at calculations for how to determine the pH in each of those regions. And so again, the 4 regions of any titration curve are as follows. There is the initial condition. Now for a strong acid or a strong base, we just converted that directly into pH for acid or POH for base, and we went on our merry way. For a weak acid or a weak base, well, for a weak acid, since we're focusing on this titration in particular, we are going to need to set up an ice table. So we're going to have to calculate, we're going to have to use Ka, we're going to have to use an ice table, figure out what the pH of the original solution is. This is pretty much the exact same kind of calculation that you had to do on the quiz this morning. Question 2 asked you to determine the pH of barbituric acid using its Ka. So that's exactly what you have to do here. Nothing new, just a new context for it. The second region is the region between our initial condition and the equivalence point. And for this, what we have created is a buffer. And since we are talking about buffers, we can use the Henderson-Hasselbalch equation to figure out what the pH of that buffer is. All that we need to do is figure out how much acid and conjugate base are present at that moment of the titration. And for that, you're going to need to set up a modified ice table, some stoichiometry, to figure out how that comes about. At the equivalence point, so at this point, we've added enough hydroxide that all of the initial acid has reacted. And so all that is left is its conjugate base. Now, since it's the conjugate base of a weak acid, we know that it's going to act basically toward water. And so we're going to have to, this is where we do the kind of calculations that we did last chapter with salts. This is basically salt equilibrium. I need to turn the Ka of the acid into the Kb for the conjugate. I need to set up an ice table. I need to solve for hydroxide in the ice table. The hydroxide gives me POH. POH can get turned into pH. Of these 4 steps, that step is the longest to take, because I've got to turn the Ka into Kb. I've got to figure out what the concentration of the base of the conjugate base is. I've got to solve an ice table for hydroxide. I've got to turn the hydroxide into POH. I've got to turn the PaOH into pH. Involved, long kind of problem. After the equivalence point, zone 4, This is actually the easiest one, because since after the equivalence point, raw hydroxide is now in the solution, all I need to do is figure out what the hydroxide concentration is and use that to figure out the pOH, which I can then find the pH from. So modified ice table stoichiometry to figure out the hydroxide concentration, direct conversion into pOH and pH. Simplest calculation by far out of these four. Although Henderson-Hasselbalch, the buffer region, would give it a run for its money as well, because the Henderson-Hasselbalch equation is easy to use once we know what the concentrations are. So the bulk of our focus today is going to be looking at these systems and just running some calculations, getting some practice. And that's what that homework assignment is all about as well. Running these kinds of calculations, getting some practice. So here is an example problem. This is one of those multi-step problems I was talking about before. This is a very common way to be asked questions about titration curves in this kind of setting, in this kind of application. We have 50 milliliters of 0.350 molar propanoic acid. Ka for propanoic acid is 1.4 times 10 to the negative fifth. We're titrating it with 0.175 molar sodium hydroxide. We want to know what the pH is at under these four conditions. Now, intuitively, why am I giving you these four conditions? Well, these four conditions represent each of the four zones. So we're going to do an example calculation here of how to calculate each one of the four zones of a titration. Understand that in a homework kind of problem, your book could just peel off any one of these and just ask you, okay, here are the titration parameters. What is the pH after 35 milliliters have been added? And what you would have to do is you would have to figure out, okay, where am I after 35 milliliters? Am I in zone 1? Am I in zone 2? Am I in zone 3? Am I in zone 4? Where am I? And the way to answer that is you do stoichiometry, you do a modified ice table, and you figure out where you are. And this is a recognition thing. This is something that you can pretty easily do over time if you get enough practice in, where you can just recognize, okay, the only time that I'm going to do the weak acid equilibrium Ka, only time I'm going to do that is at the beginning of the reaction. So that's always a V equals 0 kind of question. But otherwise, I would evaluate each one. Okay, do I have both conjugates present? Well, if I do, then I know I'm in the buffer region. And so I figure out what the concentration of each conjugate is. I plug that into the Henderson-Hasselbalch equation. I go from there. Do I have excess hydroxide? Well, if I have excess hydroxide, then I know that I'm in zone 4. I just need to figure out what the concentration of that excess is, calculate the pOH and pH directly. Do I have no excess hydroxide, but also no weak acid left anymore? Well, then I'm in zone 3. I've got to do salt analysis, basically. So let's set up, and I've got a couple of slides here that I can add on to. Let's set up where we are. And so the first one's actually relatively easy. This is just a weak acid equilibrium question. And so our initial concentration of the propanoic acid is 0.350 molar. We have no hydronium, no propanoate initially. We're going to lose some amount of propanoic acid, gain some amount of each of the products. And so at equilibrium, we have 0.350 minus X for the concentration of the propanoic acid, X for the concentration of hydronium, X for the concentration of the propanoate. Setting up our equilibrium expression, 1.4 times 10 to the negative fifth is equal to X times X over, well, let's stop ourselves here. Can we ignore the minus X term here? Is this a 5% candidate? Yeah. We have a relatively high concentration of the propanoic acid, and Ka value is kind of middling, 1.4 times 10 to the negative fifth. If we did the calculation, we get 0.004%. So we're pretty safe to ignore the minus X term. And because of that, that makes this relatively simple by comparison. No quadratic to solve. Ka times 0.35 is 4.9 times 10 to the negative sixth. Square root 2.2 times 10 to the negative third is our concentration for X. So that means that the hydronium concentration is 2.2 times 10 to the negative third molar. We can calculate the pH off of that directly. And to 2 decimal places, we get 2.66. So there we have it. That is letter A. That's our first calculation. Pre-titration, we expect a pH of 2.66 based off of the concentration and the Ka for the propanoic acid. All right, let's look at the next one. So in this one, we are adding 30 milliliters. Okay, so for every other problem aside from the initial condition, we're going to have to do stoichiometry first to figure out where in the titration curve we are. Obviously, we're not in zone 1 because zone 1 is before the titration even begins. But where are we in terms of the rest of it? And so we're going to set up a stoichiometry here. Our propanoic acid reacting with hydroxide to make water and the propanoate ion. And again, chemical formulas here aren't nearly as important as what those things mean. We have to understand that the H prop, our propanoic acid, is our acid, and that prop minus, the propanoate ion, is our conjugate base. So once again, we're going to use the millimole technique to set up our initial conditions and see where we are. So 50 milliliters times 0.350 molar is 17.5 millimoles. For the hydroxide, 30 milliliters times 0.175 molar is 5.25 millimoles. And we're starting initially with no conjugate base. So that's our initial condition. Our change condition, limiting reactant takes over. So we're going to lose 5.25 of all reactants. And we're going to gain 5.25 of our product. And so at our new equilibrium set, 17.5 minus 5.25, rounded to 1 decimal place, is 12.3 millimoles. We have no hydroxide left over. We have 5.25 millimoles of the propanoate. We started with 50 milliliters. We've added 30 more, so this is now 80 milliliters of solution. And so our new equilibrium concentrations, 12.3 divided by 80 is 0.154 molar. 5.25 divided by 80 is 0.0656 molar. Where are we in the titration? What do we have right now? It's not just weak acid, so we can throw that out. We have no free hydroxide, so that's zone 4. Do we have a buffer or do we have a salt solution? We have a buffer, yeah. We've got not equal amounts, but we have considerable amounts of each of the conjugate species. So that's a buffer. Since it's a buffer, we would use the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of concentration of base over the concentration of acid. So the negative log of 1.4 times 10 to the negative 5th plus the log of the base, 0.0656, divided by the acid, 0.154. 1.4 times 10 to the negative 5th, the logarithm of that, 2 decimal places, 4.85. 0.0656 divided by 0.154 is 0.426. The logarithm of that is negative 0.371. Adding those together to 2 decimal places, we get 4.48. So considering that we started at 2.66, 30 milliliters into the titration, we have crawled up to 4.48. Now, mind you, remember the difference between the strong acid and the weak acid titration. The strong acid titration would probably still be hanging around pretty close to where it started. If it started at 2, it'd probably be at like 2.5 right now. It'd be very, very close because the neutralization would just knock out free hydronium. There'd still be plenty of free hydronium left over. Instead, we're going to see this gentle crawl upward in pH because of the fact that we have a buffer system in place. All right, so that's zone 2. All right, questions with how we did that? So let's look on to the next case. The next case had us adding 100 milliliters of this solution. Like with every other scenario here, as soon as we start adding that base, we need to set up a stoichiometry to figure out where we are in the equilibrium. So similar to what we did in the previous, we have the propanoic acid reacting with hydroxide to make water and propanoate ion. Our initial condition, since we already did it in the previous problem, we can just extend. It's still, we started with 17.5 millimoles of the propanoic acid. And we had none of the conjugate base. 100 times 0.175 is 17.5. So here's where we have kind of a peculiar situation. From a stoichiometry limiting reactant standpoint, they both run out. 17.5 for each of them, so 17.5 millimoles here, 17.5 millimoles here. 17.5 millimoles of product as a result. Subtracting out, I have no propanoic acid. I have no free hydroxide. I only have 17.5 millimoles of the propanoate, the conjugate base, and that is now floating around in 150 milliliters of solution. So our concentration of the conjugate base at this spot is 0.117 molar. So at this point, we would have to recognize I have no acid, I have no hydroxide, I only have the conjugate, I'm at the equivalence point, and at the equivalence point, I'm dealing with a salt solution. So all that's left in there is the propanoate ion. And the propanoate ion, since it's derived from a weak acid, is going to be basic. So we need to set up a second equilibrium. The equilibrium expression that we want is what happens when that propanoate ion interacts with water. And we know that the answer is it acts as a base. So the product of this reaction is going to be the propanoic acid and, more importantly, hydroxide. The equilibrium constant for this one times 10 to the negative 14th divided by the Ka for propanoic acid, 1.4 times 10 to the negative 5th. Kb is equal to 7.1 times 10 to the negative 10th. So is this the strongest base you've ever seen? No. But is it going to be enough to push the pH beyond 7? Absolutely. Now we just need to figure out how far beyond 7 we're talking. So we've got to set up an ice table. Initial concentration is 0.117 molar. So we just keep setting up the ice table like we have been. With Kb being that low and the propanoate concentration being that significant, we know that we can ignore the minus X term here. It's not going to play in. So we're setting up 7.1 times 10 to the negative 10th is equal to X times X over 0.117. 7.1 times 10 to the negative 10th multiplied by 0.117 is 8.3 times 10 to the negative 11th. Taking the square root, we get 9.1 times 10 to the negative 6th molar as X. And so that would be our hydroxide concentration. From that, we can derive the POH. So POH would be 5.04. pH would be 14 minus that, which would be 8.96. So like I said, not the most basic thing you've ever seen, but certainly significantly above 7 enough that if you were plotting this titration curve, you would absolutely notice it. So this is the longest calculation that you can do off of a titration curve. And it's no surprise why. It's you've got to figure out where you are using stoichiometry. Stoichiometry tells you you have to make a new equilibrium. New equilibrium has to be solved, and then you have to convert to pH. It takes a while to get there. It took the entire slide to kind of write all of this through. But the real key to it is you have to know where you are. All right, last example for this particular problem. Where are we at 130? So Now we're at 130 milliliters of the 0.175 molar sodium hydroxide. Just like with the previous two problems, we need to start with stoichiometry. So propanoic acid reacting with hydroxide to make water and propanoate ion. Now, given the context of what we've already done, we know how this story ends. Because we know that the equivalence point was at 100. This is above 100, so we're going to be dealing with a hydroxide overload here. But if you're doing this independently, you would still need to follow the calculations and figure out where you are first. So we know from the other problems that we started with 17.5 millimoles of propanoic acid and none of the conjugate. $130 times 0.175 gives us 22.8 millimoles of hydroxide. Using our limiting reactant, we have less propanoic acid, so that is our limiting reactant. So at the end of this, we have no propanoic acid, 22.8 minus 17.5. We have 5.3 millimoles of the hydroxide. We have 17.5 millimoles of the propanoic acid, or sorry, the conjugate base, propanoate ion. Okay. Even though we know that the propanoate ion is basic, because we have free hydroxide in here, we no longer care about its basic qualities. And the reason we don't care is because the free hydroxide is going to have a far greater impact on the pH than that amount of conjugate base spin. And if you think about it from a Ka, Kb standpoint, Kb for hydroxide is 1 times 10 to the negative 7th. That's nearly 4 orders of magnitude better than what we just calculated. So, we're going to get far more impact here. 130 plus 50 is 180 milliliters. So we do not need to worry about the concentration of this since we have free hydroxide. That no longer matters to us. 5.3 divided by 180, the two significant figures is 0.029. Since we have free hydroxide, we can immediately go into pOH calculations. pOH is equal to 1.54, which means pH being 14 minus that. $12.46. We are going to see that kind of impact regardless. So yes, it's 30 milliliters extra from where we were, but even at milliliter number 1, we were going to see some kind of an impact. Yeah, at 1 milliliter over, the pH would have jumped to 11.06. So at the equilibrium point, it was 8.96. 1 milliliter over, it would have jumped to 11.06. 30 milliliters over, it's now 12.46. Free hydroxide always trumps conjugate base. So the moment that we go past the equivalence point, we no longer care about that other equilibrium, because free hydroxide is always going to win out. Okay, so that is a very long, kind of tortured problem. But I wanted to highlight each of those 4 different kinds of calculations. Any questions about those calculations themselves? Okay. So I really haven't shown you anything new or different. It's just doing the same thing in a different application. And the stoichiometry component of it is merely there to tell you what the next calculation is going to do, what the next calculation is going to be. And that's really the challenge in a titration curve kind of calculation, is figuring out, where am I in the titration curve? What is the next thing that I have to do? All right. Here's a simpler example. So in your homework set tonight for the weekend, you're going to see problems like this mixed into some of those multi-step problems as well, because I want you to get familiar with both kinds. So here we have 50 milliliters of 0.1 molar acetic acid titrated with 0.1 molar sodium hydroxide. What is the pH of the solution after 50 milliliters has been added? And so right away, we recognize this is a titration. I've got a strong base and a weak acid. First thing that I need to do, figure out where in the titration I am. Now, Ka for acetic acid, we've worked with it numerous times. It's 1.8 times 10 to the negative fifth. But before we can even determine if we need that, let's figure out where we are. Initially speaking, 50 milliliters times 0.10, that's 5.0 millimoles. 50 milliliters times 0.10, that's 5.0 millimoles. Okay, I think we can see where we're going here. So right away, I recognize I have equal molar amounts of the acid and the titrating base. Limiting reactant tells me I'm going to lose 5 of each of the reactants, gain 5 of the product. So at this particular spot, I have no acid, I have no hydroxide, and I have 5 millimoles of the acetate ion now running around in 100 milliliters. So 5 divided by 100 is 0.050 molar. So we would have to recognize out of this particular practice problem, all right, I'm at the equivalence point. So I've got to do pH of a salt solution. Because that's basically what this is now, right? If I carry out the, if I set this up like a double replacement reaction, I get water and sodium acetate as my product. So at the equivalence point, since I have neither of these two starting materials and all product, that solution at that particular point is water and sodium acetate. It's a salt solution. And as a salt solution, we've got to go through and do pH of salt calculations. So knowing that we have acetate ion, it's going to react with water in an equilibrium kind of way. And produce hydroxide. We've got to set up our second ice table here. 0.050 molar is the concentration. We have no hydroxide and no acetic acid, and that's evidenced by the above ice table as well as just logic here. We're going to lose some amount of acetate, gain some amount of acetic acid and hydroxide. And so at equilibrium, those are our concentrations. X for each of the products, 0.050 minus X for the acetate ion. Now here's where that Ka value comes in. Because right now I don't have an equilibrium constant for that ice table. Yeah, I know I need one to solve it. To find Kb for the acetate, I need to take 1 times 10 to the negative 14th and divide it by the Ka, 1.8 times 10 to the negative 5th. And I get 5.6 times 10 to the negative 10th. So setting up my equilibrium calculation, 5.6 times 10 to the negative 10th is equal to X times X. Even though this is a lower concentration of the acetate ion at 0.05, this being 10 to the negative 10th, we're going to be able to ignore that minus X term pretty easily. 0.050 in the denominator. 5.6 times 10 to the negative 10th times 0.05 is 2.8 times 10 to the negative 11th. Square root of that, 5.3 times 10 to the negative 6th. And since X is our hydroxide concentration, we can immediately figure out POH. So negative log of 5.3 times 10 to the negative 6th is 5.28. Which gives us a pH of 8.72. All right. So this is an example of a single question that you could be asked about equilibrium, about a titration curve. And it always starts up here, doing this stoichiometry, doing this modified ice table to figure out where you are. Once you figure out where you are in the titration, then you can adjust from there. And like I said before, this particular brand of calculation is the most difficult. And the reason it's the most difficult is because it's the longest. Because in addition to doing the stoichiometry, you've got to flip around the equilibrium, you've got to calculate a new value for K. There's lots of stuff that you have to do and lots of little mistakes that you can make along the way. All right, any questions with this example? All right. Well, since it's acid base, since we're talking about titration, there's not really a synthetic part of it. Double replacement is what titrations are. And so with double replacement, you're going to have two reactants turning into two products. Could you do that first stoichiometry table with only three parts? You could. You could ignore the water term since it doesn't play into it. And for titrations that are going the opposite direction, where we have base and hydrogen coming together, oftentimes that will just be omitted because the conjugate acid is just the synthetic adduct of those two. But since we are dealing almost exclusively in this case with acid-base chemistry follows a double replacement pattern. All right, other questions here? All right, I'm going to have you try one for yourself here. We have a 25 milliliter sample of 1 molar hydrofluoric acid being titrated with 0.50 molar sodium hydroxide. What is the pH of the solution after 25 milliliters have been added? And for reference, we've given you the value for Ka here. So go ahead and take a moment here and figure out what's going on, where we are in the titration, and most importantly, what the pH is when we complete that. All right, so as has been the case with really all of the questions that we've been dealing with today, the primary question is, where are we? And to answer that question, we need to set up a stoichiometry so we need to set up a modified ice table like we have with the past. And so starting with our hydrofluoric acid, 25 times 1 would be 25.0 millimoles of HF. And with half a mole or half a molar, 0.5 times 25 of the NaOH, we get 12.5 millimoles of the hydroxide, with fluoride standing at 0 currently. Limiting reactant takes over, so we're going to run out of the hydroxide first. So 12.5 off of each. Means that we have 12.5 millimoles of HF, no hydroxide, and 12.5 millimoles of the fluoride. This is now in 50 milliliters of solution. Now, one thing that we can recognize is that the two concentrations here are going to be identical. 12.5 divided by 50 for each. So 0.25 molar for both. But now it comes recognition time. Okay, well, where are we? I have considerable amounts of each conjugate present. By definition, that's a buffer. Henderson-Hasselbalch equation needs to be where I go. So pH is equal to pKa, the negative log of 7.2 times 10 to the negative fourth, plus the log of the base concentration, 0.25, divided by the acid concentration, 0.25. And so mathematical recognition here, if I have the fraction where they're equivalent, 1, log of 1 is 0, pH is equal to pKa here, which would be the negative log of 7.2 times 10 to the negative 4, 3.14. And that's all it would be. If the values in the ratios were different from each other, we would have to obviously calculate that log out. But as it stands, this is all that we needed. And so, again, the important thing out of these kinds of problems is if you set up the calculation correctly, you just have to figure out where you are and what that second calculation looks like. So recognizing that I have a buffer, I can immediately go into Henderson-Hasselbalch, and I can kind of take it from there. All right, questions in this example? All right, I've got a different question for you here. So this is just a general titration curve kind of question. I've got 0.1 molar solutions of these 4 different acids. I'm titrating them all with the strong base, sodium hydroxide. Based on the strength of the acid, rank the pH of the equivalence points in increasing order. So put the one that's going to have the highest pH at the top, the one that's going to have the smallest pH on the bottom. So the answer to this question really comes down to, do we understand our conjugate theory? Obviously, with the hydrochloric acid, since this is a strong acid, the pH is going to be equal to 7. All of these are going to be pH greater than 7 because they're all weak bases otherwise. So we know that HCl goes on the bottom. Now it's a matter of, do we understand the theory? And the theory is that conjugates are inverses of each other. The stronger the acid is, the weaker its conjugate base is going to be, which would mean it'd have less of an impact on pH. And so if we take them in order of strength, then what we would see is that, okay, nitrous acid is the next strongest. So the nitrite ion is going to have a basic pH, but it's probably going to be in the high 7s, low 8s, maybe mid 8s, depending upon concentration. From there, the hypochlorous acid would be the next strongest with its Ka. Its hypochlorite ion is actually a better base than water, than hydroxide. So we've got that going there. And then hydrocyanic acid, HCN, would be the worst of the acids, the weakest of the acids, which means the cyanide ion is actually the strongest of those conjugates. And so that would be the correct order: hydrocyanic acid on the top, hydrochloric acid on the bottom, and hypochlorous and nitrous in between. Any questions with the theory here? Okay, so before we completely put this away, every example that we've done thus far has been weak acid in the flask, strong base being titrated into it. What we have to understand is that the reverse is possible as well. I can have a weak base that I'm titrating a strong acid into. And for that, the titration curve looks the same, only reversed, kind of similar to what we saw for strong acid, strong base versus strong base, strong acid. We're starting at a high pH, we're ending at a low pH, and the main difference between is, again, we've got a buffering zone up here. And an equivalence point on the acidic side for the weak base equilibrium. But what we see is that mirror images of the kinds of calculations that we have to do inside of these kinds of titrations compared to the ones that we just did. So the same 4 zones apply to a weak base titration as they did to a weak acid titration, just slightly changing the perspective because we're looking at a base instead of an acid. So the first zone is still the initial pH. It is still governed by an equilibrium constant and an ice table. Only we're focusing on Kb instead of Ka because it's a base, not an acid. Zone 2 is still a buffering region. The only difference is that we're going to use the base dominant Henderson-Hasselbalch equation instead of the acid dominant one. Zone 3 is still salt equilibrium. The only difference is that we're going to be focusing on a conjugate acid salt instead of a conjugate base salt. After the equivalence point, we're going to be looking for free hydronium or free hydrogen ion as opposed to free hydroxide. So every calculation is exactly the same. We're going to handle it in the exact same manner. Start with stoichiometry, figure out where we are in the titration, move on from there. The only difference is from a perspective standpoint, we're looking at it through the opposite side of the mirror. Everything that was pKa and Ka based now becomes pKb and Kb based. When we were looking for hydronium or hydrogen before, we're now looking for hydroxide, and vice versa. So let's do one example of this together, and then we'll call it a week from here. So I've got 25 milliliters of a 0.109 molar solution of morphine. We're titrating it with 0.1011 molar sodium hydroxide. Question is, what is the pH of the solution after 17.8 milliliters of base have been added? If you're looking for this in the PowerPoint notes, it's not there. I made it while you were working on the last problem. And the reason I did was the last top hat question was a true-false question, and they had no example problems of going the opposite direction. And you need to know how to go the opposite direction. So setup-wise, same setup that we were talking about before. And I do need to make one change here. Morphine is a base. So we need to titrate it with an acid. And I forgot to put the Kb value in. So Kb for morphine is 7.4 times 10 to the negative 7th. I'd say that is my biggest complaint about PowerPoint compared to others is that this font. All right. Okay, so now you see the problem with making practice problems on the fly. Sometimes you forget things. Okay, so the chemical formula of morphine, again, I've given it to us here. It's not terribly relevant. We could just set up a stoichiometry that looks like this and be perfectly fine. We could also use abbreviations if we wanted to. It doesn't affect the interpretation of the end result here. If we wanted to get technical, C17H19O3N plus hydrogen ion makes C17H19O3NH plus. But again, in terms of our understanding of what the problem is asking us to do and And the actual results, we've been using abbreviations for an entire week here because it doesn't matter that much. Setting up our ice table. 25 times 0.109 is 2.73 millimoles. 17.8 times 0.1011 is 1.800 millimoles. And we have no product at the start here. So we're gonna lose some, we're gonna gain some. Hydrogen ion is the limiting reactant, so 1.800 is what is lost. And 1.800 millimoles is what is gained by the acidic form of morphine. So at this point, I would have 0 hydrogen ion, 2.73 minus 1.8000 or 00 to 2 decimal places is 0.93 millimoles and 1.800 millimoles. So what we should be able to see at this particular juncture, we do have a buffer solution. We just need to figure out the concentrations. So 25 plus 17.80 is 42.80 milliliters. So our concentration of morphine at that point is 0.022. And our concentration of the acidic conjugate acid is 0.04206 molar. So we should recognize at this point we have a buffer solution. We have significant amounts of conjugate acid and conjugate base present. And so we're going to use the Henderson-Hasselbalch equation here. And so for the Henderson-Hasselbalch equation, since we are dealing with a base, we have one of two options. Option one is that we could turn this Kb into a Ka value and use the Henderson-Hasselbalch equation as normal. That would be option one. Option two is that we use the base version, the POH version of the Henderson-Hasselbalch equation. And that would require us to do no conversion other than the conversion from POH to pH. Each one has their advantages. You can go either direction. To do the Ka conversion, it would be 1.0 times 10 to the negative 14th over 7.4 times 10 to the negative 7th. And you get 1.4 times 10 to the negative 8th. And so you could take that, throw that into the Henderson-Hasselbalch equation, do base over acid, you would be just fine. Let's go ahead and use the POH version, though, just to see it in action. So the negative log of our Kb plus the log of the acid, 0.04206, divided by the base, 0.022. So the PKB is 6.13. 0.04206 divided by 0.022 is 1.9. The log of that is 0.28. So the POH 6.13 times, or excuse me, plus 0.28 is 6.41, which means the pH is 14 minus that, which would be 7.59. Like I said, you could solve this using Ka if using the traditional form, the Henderson-Hasselbalch equation, you'd get pretty much the same result. But this is an example of how to handle, well, what if I have a weak base that's being titrated instead of a weak acid? The answer is you pretty much do the same thing. Set up your stoichiometry, figure out where you are, and then based on where you are, that's how you do the second calculation, that based off of that adjustment. All right, any questions with this problem? All right, then the last notes I'm going to make here are just more from a kind of a general knowledge perspective, just the idea that you can draw titration curves for polyprotic acids. So for things like sulfuric acid or phosphoric acid, this is actually a titration curve for sulfurous acid, and you can see both equivalence points there. Yesterday in lab, you did the titration curve for phosphoric acid for the first two equivalence points. And what you see in these kinds of curves is that you get multiple equivalence points, you get multiple buffer regions. The sulfuric acid titration curve is actually a unique one because it's two equivalence points. The first one, the first part of the curve looks like a strong acid curve because sulfuric acid's first deprotonation is a strong acid deprotonation. And so it starts very flat and then jumps real quick. And then when it jumps there, because bisulfate HSO4 negative 1 is a weak acid, then it starts to buffer. And then we get more of like a weak acid curve for the second equivalence point. For sulfuric acid, the one that's in the picture here, since it's weak acid from the start, then we get two weak acid curves basically. One important thing to make note of though, if we are evaluating half equivalence points, remember one of the things I said yesterday was half equivalence points because in that part of the buffer region, the acid-base ratio is identical. pH and pKa are the same value. We can use that for identification purposes, but we have to understand in a polyprotic acid kind of sense, the half equivalence point we talked about would be here for the first one. So the first equivalence point was here at 25. The half equivalence point for the first would be here at 12.5 milliliters. Understand that for the second equivalence point, the half equivalence point is not halfway. I can't look at the second equivalence point here and say, okay, well, the half of 50 is 25, so the equivalent, that it's not there. Each equivalence point gets evaluated individually. So it took us 25 milliliters to go from 0 to the first equivalence point. It took 25 milliliters to go from the first to the second. The half equivalence point would be halfway between the two equivalence points here. So 37.5 milliliters. So if you're ever put in a situation where you are trying to identify an acid based on its pKa, or identify a base based on its pKb using a titration curve, what we have to understand is that if it is polyprotic, that half equivalence point is between, basically halfway between whatever two equivalence points we're looking at. So if I'm starting from 0, it's halfway to the first equivalence point. If I'm looking at the second equivalence point, it's halfway between the first and the second, halfway between the second and the third, if I was looking at a triprotic. And that's where we're going to stop for today. So Monday's class is going to be all about solubility equilibria. It's going to be all about how do we determine if something is soluble or insoluble in water? How do we calculate just how soluble it is? And what are some things that impact the solubility of a solid in water, both in a positive way as well as in a negative way? But that will be what we do on Friday, or excuse me, on Monday.